Now, morphogenetic fields must be inherited. Foxglove plants give rise to foxgloves, hedgehogs give rise to hedgehogs, skunks give rise to skunks, giraffes give rise to giraffes. The forms of these organisms are inherited, and I've been arguing that I don't think this happens through the genes. The genes are just about protein synthesis and turning on and off protein synthesis. The forms have to be inherited some other way. Now, this is my own particular take on morphogenetic fields, and the hypothesis is that they're inherited by the process I call morphic resonance, a resonance across space and time based on similarity. For example, the patterns you've just seen on the cymoscope are resonant patterns, and there could be resonance across time involving patterns of that kind. The patterns within a developing foxglove or a developing giraffe should resonate across time so that a present-day giraffe, growing as an embryo in the womb of its mother, is resonating with previous giraffes which have been developing in the wombs of their mothers and growing into adult giraffes. And this resonance carries the form of the field of the giraffe, the morphogenetic field. It carries it as a kind of average or composite of many previous giraffes, millions of them, a bit like the composite faces we saw. So I think morphic resonance is a fundamental principle of memory in nature. I'm not supposing that this is just something confined to biology. I think it's part of the way nature works. I think the way crystals crystallize depends on morphic resonance as well. The first time you make a new chemical compound into a crystal, it won't have a pre-existing morphogenetic field. But if you make it again, the second time it should happen faster than the first time because there'll be an influence from the first crystals by morphic resonance. The third time it should happen easier still by influences from the first and the second crystals. The fourth time from the first, second, and third, etc. There'll be a build-up through morphic resonance of memory, making it crystallize quicker and quicker. And newly synthesized compounds are indeed very often hard to crystallize to start with. People wait weeks or months before they crystallize, and then they crystallize easier and easier as time goes on. In most general terms, this hypothesis suggests that the so-called laws of nature are more like habits. The usual assumption within the sciences is that the laws of nature were all fixed at the very moment of the Big Bang, and they've been the same ever since. This is, I think, a very unjustified assumption. In an evolutionary universe, it makes much more sense to think of the laws of nature as themselves evolving. And I think that's what's indeed happening. I discuss this in detail in the Presence of the Past, and also in my most recent book, Science Set Free, which is called The Science Delusion in the British version. This hypothesis provides all sorts of opportunities for empirical tests. One is with crystals, as I just mentioned, but there's another test with crystals, which I'll now very briefly discuss. If crystals become more stable as the habit of forming that crystal becomes stronger, then it should be harder to break them up. They should not only form more easily, they should be harder to break up. Now, the way you break up crystals is by heating them, and you reach a particular temperature at which the structure dissolves, it's lost. That's, of course, called the melting point. I'm predicting that newly synthesized compounds should show rises in their melting point. But compounds that have been around for millions of years, crystallizing in nature, will have so much morphic resonance from the past, they'll behave as if they're governed by fixed laws. They won't show these memory effects that new ones do have, because there'll be such a vast backlog of morphic resonance from the past. So I've done some research on the history of melting points, and I've compared melting points of substances that occur in nature with synthetic related compounds that were first made by chemists in the 19th or the 20th century. The next slide shows some of these examples. On the left, we have compounds that occur in nature. On the left, at the top, salicin occurs in willow bark, crystallizes in nature. No change over the 20th century. These are in 3 dates in the 20th century. On the right is aspirin, acetyl salicylic acid, a synthetic compound first made in the 19th century in Germany. And over the 20th century, the melting point has gone up quite considerably. We're talking here increases of 7, 8, 9, in some cases 15, 20 degrees centigrade. We're not talking fractions of a degree. Then we have penicillic acid, which occurs in nature in exudates from molds. And on the right, penicillamine, used as a chelating agent, or it's also a breakdown product of penicillin, which is a synthetic form of what occurs in nature. There again, that has shown an increase in melting points, but the natural form hasn't. At the bottom, we see on the left cocaine, which occurs in coca leaves and has been crystallizing in dried leaves for millions of years. No change in the 20th century. On the right, we see cocaine hydrochloride, which is the cocaine of commerce made by extracting coca leaves with hydrochloric acid. It doesn't occur in nature, and the melting point of that has gone up by about 9 degrees over the course of the 20th century. It's possible to test for morphic resonance in the realm of developmental biology as well. And I'll just give one example. The next slide shows at the top a normal fruit fly, Drosophila. And the normal fruit fly has 2 wings, like all flies. And in the segment below the wings, it has what are called Holt hairs, balancing organs. The lower example shows a mutant fruit fly where the Holt hairs have been transformed into wings. So it's got 4 wings instead of 2. This is very like the example I gave earlier of pea leaves, where the same bud, as it were, could turn into a leaflet or a tendril. And there are some mutants where what are normally tendrils turn into leaflets, and then some where what are normally leaflets turn into tendrils. It's that kind of mutant. The technical name for these mutants is homeotic mutants. Well, it's as if the gene affects the tuning of the system and throws a switch so it tunes into a different morphogenetic field. Well, it turns out that with fruit flies, you can produce the same effect as a homeotic mutant just by changing the environment. No change in the genes. If you expose the eggs of fruit flies to ether, diethyl ether, 3 hours after they're laid, a few of the resulting flies have 4 wings instead of 2, usually only about 2%. If you expose their eggs to ether, then a higher proportion have 4 wings instead of 2. And if you keep doing this generation after generation, the proportion of 4-winged flies goes up. The next slide shows an experiment of this kind. The bottom axis is the number of generations that they've been treated, the eggs have been treated with ether for, and the vertical axis shows the percentage of 4-winged flies in the population. The dotted lines going down to the right are where they stopped treating the eggs with ether, and the proportion of 4-winged flies fell off. It didn't plummet down to 0 straight away, though. It carried on for quite a few generations at a decreasing rate. Now, this could be an epigenetic inheritance effect. Epigenetics is a form of inheritance of acquired characters, which was until recently highly taboo within biology, but is now intensely fashionable. But I think something more interesting is going on here. I think it's a morphic resonance effect, as well as an epigenetic effect. And the key experiment here is that the experimenters took some fruit flies whose ancestors had never been exposed to ether, and after they'd done the first experiment, they did a second experiment. Now, if you look at the left, the first time round, the first generation treated with ether had about 2% of the 4-winged flies, the second generation about 6%. But the second time round, you'll see the line above that with the filled in points. The first generation had 10%, and the second generation 20% of these 4-winged flies. I think that's because morphic resonance from the first lot of flies had made it easier for this abnormal pattern to appear again. I should emphasize again, this has nothing to do with changes in the genes. It's to do with a developmental disturbance, more like the effects of thalidomide on human embryos, causing developmental abnormality because of the conditions in which the embryo grows. Now, if four-winged flies had a great evolutionary advantage, then morphic resonance would make them appear more frequently, give them and could accelerate the whole evolutionary process. In fact, they don't have an advantage, so this effect's only seen in highly artificial experiments.